First, I want to thank Professor Ferro and you, Luca, for the very kind invitation. I'm very happy to be here and also to see what the Italian group on fatigue is doing. And what I have seen until now was really respectable work, and also from the titles of the program what I have seen, very new things, and I encourage you to continue in this direction. Now, with regard to my talk, I want to talk about the structural durability assessment of offshore K-Nodes by contrasting different local design concepts. The question of offshore K-Nodes is again something which gains actuality, especially with regard to the energy problems, wind energy, and also all these things related with that. And these K-Nodes are essential parts in the jacket of such structures. You see it, you can recognize it. These are these parts which are welded in form of K-Nodes. You can see it here, or in conventional oil board platforms you can recognize here. These are these structures, and certainly they are complex loading. It is not only fatigue loading, not loading only with variable amplitudes. We have also the environment causing also corrosion, and we have to see how to work with that. Now, the results that I am presenting to you, or let's put it in that way, the basis was determined end of the 80s, beginning of the 90s. We had a very big program on offshore K-Nodes of the European steel industry. At that time, certainly, the evaluation was carried out with the methods of that time, of 20 years ago. And now we have today also modern methods. And as these results at that time, the investigations were done very meticulously with strain gauges and all what was necessary, so they could be re-evaluated with modern concepts. And this is what I'm doing again here, what I'm presenting to you. Now, with regard to design concepts in structural durability, we had already spoken in the afternoon about these concepts. We have different concepts. The nominal stress concept. This is the classical concept, but it is only applicable if we are able to define a nominal stress. If we have a complex structure, or if we have complex failure locations, and if we are not able to define nominal stresses, so it is useless to try to apply it. The second condition for the application of the nominal stress concept is certainly also to identify a notch case, a notch detail, a weld detail. This belongs also to that. I am today not talking about the nominal stress concept, because you will see in the structures that I am dealing, you cannot define a nominal stress. So, this was the reason why the structural stress concept, or called the hotspot concept, was developed for compensating the lags coming from the nominal stress concept. But also the structural stress concept, which I will treat also, has some shortcomings. It cannot evaluate, for example, hidden weld notches, slits, etc. Therefore, in the continuation, it is always, all these things are in a logical continuation, it's a logical chain. Then the local concepts, as also Paolo Lazzarin introduced in his K-Node lecture, were introduced. I will treat here the local notch stress concept. There are also other variants. And certainly we have also the fracture mechanics concept. With regard to stress intensity and related energy, Paolo Lazzarin treated that. In my presentation, I will show you results and calculations of crack propagation. So I will treat these concepts which I have presented here. Very shortly, about what we are talking, the structural stress concept. I'm not treating the structural stress concept with this value just close to the weld notch, which was also treated in one of the presentations, this old concept of HIBA. I will treat here the hotspot concept. The hotspot concept, this hotspot stress, it was also explained. It is gained if we make here the stress analysis outside of the weld detail. Then there are some rules by which you can extrapolate the structural stress to the weld toe, and then you have to evaluate this stress. But if you have a hidden notch, for example, if you have here a not fully penetrated well, and if the critical area is here, so you cannot make with this value anything, you cannot extrapolate it to this area. So what you have to do is to determine for this area a notch stress. This shows you schematically how you can put the reference radii in the different notches, especially in these areas you cannot capture these points by the hotspot stress concept coming from outside. And with regard to this reference radius, also Paolo Lazzarin explained to you the hypothesis which was behind. It is the micro-strength hypothesis of Neuberg, which was varied by Radai, where he derived the value of 1 millimeter notch radius. Certainly this radius has also, the application of this radius has also a limitation. You can apply this concept only to thicknesses upwards than 5 millimeter. If you are at 5 millimeter, you come into a conflict situation, so you have to make some compensations which don't function every time. And if you are lower, if you have thin sheets, so you have to go to the 0.05 millimeter concept, which has a fracture mechanical background. But I'm not treating this. If you are interested in the 0.05 application of the 0.05 millimeter radius, then come to Venice to the Eurojoin. There I will give a paper where I'm treating with various examples this concept. Now let's talk a bit about the design which has to be assessed here. So these K-Nodes have this shape. Here you see the wells. These are huge, well, what we have tested were not small specimens, were huge structures. You see here 4 meter long. We have here a diameter, a radius of 1 meter, a thickness of 30 millimeter. This is the core. And we have here the braces loaded in this direction, actually. And the diameter of the cores was 500 millimeter, and the thickness was 20 millimeters. So thick, big structures. And the critical areas, I can show it also to you. They were here. That means if you come up here with the load from the braces, you cannot define here a nominal stress for this area. So you have no other choice than to apply here the structural stress concept or local stress concept, and certainly also the fracture mechanics concept. What you see here are also the strain gauges, which were also applied additionally to the calculations in order to verify also what was calculated. The steel was the fine-grained steel, FAE 355. This is a steel grade which is used in ship industry, in offshore industry very often. Now such offshore structures are seeing a variable amplitude loading in the North Sea. The load comes from the waves. And what you see here is overall spectrum for 1 year. It contains 10 different sea states. Low sea states up to very high sea states. Every sea state has a Gaussian distribution, but when you superpose Gaussian distributions, you end up with a straight line distribution. What you see here is also an omission. In 1 year we have about 5 million cycles, because the frequency of the waves is not high. So you come up to 5 million cycles, but if you want now to carry out your test and you have to repeat this spectrum, this sequence, and if you have here a total of 5 million cycles and you must repeat more than 25 times, because for an offshore structure the required fatigue life is at least 25 years. So you will never end up with this test, so you have to make here an omission, a non-damaging omission. That means omitting some amplitudes which don't omit in order to make your test in a shorter time. So far to the spectrum. Now to damage accumulation. What we apply here is the Palmgren minor rule. Please don't say minor rule. Before minor it was Palmgren. I think everybody knows how to apply the Palmgren minor rule. But what we do is here the damage sum. We don't apply here the damage sum 1. Already also in the IIV design recommendations it is written. The damage sum to be applied is 0.5. This is based on a lot of investigations carried out in the past 30 years. if you apply to damage sum 1, 90% of all published results under variable amplitude loading are on the unsafe side. So the recommendation coming from LBF, and now it is part of the IIV recommendations, please apply 0.5. So far to damage accumulation. This is the test rig. Here you see the big structure. Here is the actuator. It is a 2,500 kilonewton actuator. Here you see the braces joined to the cord. And you see here also a basin. This basin is filled with artificial seawater with North Sea conditions. That means we have here a pH value of 7 and permanently a temperature of 15 grades. Certainly in the North Sea the temperature goes also more down, but for corrosion it is important to have the higher temperature and not the lower temperature. And so you see here with these elements, the actual loads are introduced here into the structure. Maximum frequency what we can carry out here is 5 Hertz only for the smaller amplitudes. We have carried out here constant amplitude loading tests, only 3, and 5 variable amplitude loading tests. The test duration is in constant amplitude loading between 4 to 6 months, in variable amplitude between 5 months and 1 year. So one institute could not achieve this task, therefore we were 3 institutes and we shared the work among us. Beside the LBF, the IABG and the Thyssen Research Center was involved in this work. Now let's have a look first to the results that we obtained, all presented first in the system of the applied load. Here we have the load range, and here we have the cycles. On this side we have here the constant amplitude loading. There are 3 tests which have been carried out. The triangles are the test results in terms of breakthrough. This is the stop criterion. It corresponds to total failure of a relative smaller specimen. But what we also registered during this test was the fatigue life through crack initiation by the potential drop technique. It was continuously registered. And the crack initiated, the technical crack initiated had a depth of 1 millimeter and a surface length of 2 millimeter. And after this point, certainly until the breakthrough, we registered also the crack propagation. I will show it. And here the black points, the circles, and the triangles are the results which we have obtained under variable amplitude. Now we can make certainly through the points, for example, for breakthrough, the mean curves. We have also here the slope of 3, so we are not in conflict also with IIV regulations, where also the slope of 3 is prescribed. And certainly these are 50% values. Afterwards, we want to evaluate the values with design curves of the IIV recommendations, which have the probability of survival of 97.7, mean value minus 2 standard deviations. So we have to transfer the mean values also to the same probability of survival, 97.7%. Here this transformation is done under assumption that we have here a scatter band of the stress of 1 to 1.50. This is a recommended value coming from HIBA, applied also in the British standard as well as in the Eurocode. So all these 50% values were, for the evaluation of the result later, transformed into 97.7% values. So far to the evaluation. I want to continue here with the prerequisites first for the evaluation. You see here schematically the design curve according to the IIV recommendations. The design curve is fixed by following points. First, FAT class is defined. This is the stress range at 2 million cycles with a probability of survival of 97.7%. Then we have the slope here of 3. 3 is certainly not a general slope. We can find in welded structures also other slopes, but if we have thick and stiff structures, we end up with this slope of 3. We come here to the knee point at 10 million cycles. This has been accepted since 3 years and introduced into the IIV recommendations, basing on a lot of evaluations of results from the LBF, from the TWI in the UK, from Exxon and from Nosce Veritas, where we see that the knee point or the changing of the inclination is about 10 power 7 cycles. In the Eurocode it is still at 5 million cycles, but here we have 10 million cycles. And after the knee point, we have still a diminution of fatigue strength. Ladies and gentlemen, please don't talk about fatigue strength or endurance limit. I have heard this several times today. We don't have an endurance limit, we don't have a fatigue strength. We have always a drop of fatigue strength. If you talk about endurance limit, you mislead engineers to think that there is really something that, and they program here also failure. So you have also a responsibility toward engineers which are not experts. So please select your wordings in a very careful. So under constant amplitude loading, after the knee point, we have here a diminution of the fatigue strength by 10% per decade. And 10% per decade means a slope of 22 under constant amplitude loading. But when we have a spectrum loading, as I have shown to you, then it is not anymore this part, this branch of the ascent curve which is used. It is used this branch of the ascent curve, which continues here with a slope of 5. It is 2k minus 1. It is the high bus hypothesis, high bus modification of the Palmi minor rule. And certainly when you make your damage accumulation, please use the damage sum of 0.5. So this is one of the prerequisites necessary for the assessments. For fracture mechanics, I want to show you also the prerequisites that we have applied here. I have shown to you that some tests were carried out in air, but the variable amplitude loading tests were carried out in the corrosive environment, the seawater. So we need here also crack propagation data obtained under seawater. So you see here the Paris lines in air and under artificial seawater. That means at same stress intensity due to the corrosion, the crack propagation is higher. I think it's logical, this is expected, and so we have to use this data. By the way, this data is applied. I'm sorry for the computer here, it is missing here. This data is obtained with a stress ratio of 0.1. I will come to that a little bit later. And the fracture mechanics model, which has been applied here, we applied first a very complicated model, but we were able to reduce it to a simple model which was as effective as the complicated model. So it is nothing else than the single edge cracked plate. Here you see dash in dash form also the position of the brace. This single edge crack plate is submitted to membrane loading and the bending loading which we have in the critical area. And if we compare here the results, the dashed line is the experimental results which has been obtained by the continuous potential drop technique measurement. And here you see the calculated result. We have here a factor of 1.5 difference in this calculation. This is due to the fact that we have carried out the calculation with the fracture mechanical data obtained with R equals 0. But the brace is loaded with R equal minus 1. But we have calculated with R equals 0. Why? Because we have to assume in that big structure, very big structure, that we have tensile residual stresses. And at least at the beginning of the crack initiation and 1-2 millimeter crack propagation, so this tensile load will dominate the crack propagation. Therefore, we have calculated with R equals 0. So far, the prerequisites that we have applied here. Now, let's come to the local concepts, to the hotspot concept and to the notch stress concept. First, the hotspot stress, it means for this we need the structural stress, was calculated with shell elements. In case of shell elements, we don't need a complicated modeling. It is simple. From these shell elements, we obtain here the linear stress distribution outside, and this extrapolated to the notch, so we have the hotspot stress. But when we want to determine here the local notch stresses, so we have to make here a submodel, and in this submodel, respecting also several conditions, we have carried out here the calculation for the notch radius, for the reference radius of 1 millimeter, so that we have obtained also here this radius. Here I have to say following: you must be careful when you make these calculations. You must be aware if you are making these calculations in the von Mises system or in the principal stress system. because according to the system what you are making, then you have to select also your allowable stresses. For R equal 1 millimeter in the IIV regulations, the value of 225 is given. This is a principal stress. But if you calculate in your notch von Mises stress, then you have to go here 12.5% down to 200. So you must be always in the same system. We have calculated, made the assessments here in the von Mises system. Now let's start, after the introduction of these prerequisites, with the assessments what we have done. I start here with the hotspot concept. Here on this axis we have the hotspot stress. All these results are now presented in the hotspot system, and here you have the number of cycles. Again, for the two criterion, crack initiation, these are the circles, crack initiation, and breakthrough, these are the triangles. Here we have on this side, it is not functioning anymore. Here on this side we have the results obtained under constant amplitude loading. And this fine line, what you see here, this is the IIV design curve for the hotspot stress concept. It has, thank you Paolo. You have another one? No? Okay, then I will stop soon. So this is the curve, the IIV design curve. It has the FAT value of 90. That means at 2 million cycles we have here 90 megapascal. This is the value which we have to take if we have load-carrying wells. But this curve, or this line, what you see here, is for air. You see here the knee point, and it goes down with 22. But what we have is corrosion. In case of corrosion, there are regulations, for example, from the German Lloyd or from Nosce Veritas, and they say if you have saltwater corrosion, then go by a factor of 2 to the right side, diminish your number of cycles by 2, but this is not enough. This is only for this region. In case of corrosion, we don't have a knee point, so the curve goes straight down, and you see in this region, the higher the number of cycles, the more severe becomes the corrosion. So we have here the basis, the SN curve, for contrasting it with the spectrum that I have shown to you, and we can make then the damage accumulation calculation, Palmgren minor hypothesis with the damage sum of 0.5, and from this curve we come to this curve. And when we look now to the results, first, the design curve, the criterion, the failure criterion of all design curves in the IIV recommendations or in the British standard or in the Eurocode are always total rupture. That means we can compare this design curve with the breakthrough of these K-Nodes. That means we compare this curve with the triangles. They are all on the safe side. And also, most of the crack initiation fatigue lives, the circles, they are also on the safe side. Only one is a little bit lower than that. So we can say that the hotspot concept for variable amplitude loading and also for constant amplitude loading, what you see, functions in a perfect way. We are here on a safe side. We are making here a safe assessment. Now let's come up to the concept with the reference radius of 1 millimeter according to the microsupport theory of Neuberg and the modification of Radai. In this case, certainly we have first to present the results in the local stress system. So what we have here is the notch stress range. Again here the cycles, the number of cycles for both criteria, breakthrough, and crack initiation. As we have here for Mises stresses, so we are not taking the FAT curve with 225, but with 200 at 2 million cycles. This is this line. This is for air. We have to transform it first to corrosion, as I have explained it to you on the previous picture. And we have certainly also to consider, also in the previous picture, we had also to consider the thickness effect, because the area where we had the failures had a thickness of 30 millimeters. The IIV values are given for 25 millimeters. So we have to compensate also this thickness effect, because the thicker, the lower also the fatigue strength. This has to be also compensated. So this is done here with this factor. And so we have here the SN curve. For constant amplitude loading, we have the spectrum, cumulative damage accumulation with damage sum of 0.5. 5, and we come up here to this curve, and you see again all points for breakthrough, even for crack initiation, are on the safe side. That means also this notch stress concept functions here in this example in a very satisfactory way. Now let's come up to the third, final concept which we have applied, the fracture mechanics concept. In this picture you can recognize this is the cord, this is the brace. The crack started here directly in the weld toe. It's a very classical fatigue failure what we had here. And this is 30 millimeters thick, this is the breakthrough. This results per here on the very right side of the points for constant and wave uploading are the experimental results which we have obtained by the potential drop measurements. And the dashed lines are the lines, the points, which we have calculated with the single edge model, single edge crack model, and the data that I have shown to you for the ambient of artificial seawater. Again, we are here on the safe side. Now, the question that results is certainly which concept is better, or how they correspond to each other. We have also to contrast these three concepts. At the end, we have certainly also to give an answer to the engineers which concept is the more reliable one. Because when we make such designs, and also such an offshore structure is also a safety structure. It has never to fail. In case that it fails, you know what happens. So we have also compared here the experimental results with the calculated results. Value 1 here means this is the ratio of fatigue lives and calculated to an experimental. Value 1 means experimental results is identical with the calculated results. If we are below 1, we are on the safe side. So what we see here, first we are with all these three concepts on the safe side. Here you see the results obtained with the hotspot stress concept. It is about a factor of 2 compared calculated to experimental value. The same also for the crack propagation concept. And here we have the impression that the notch stress concept is even more conservative. But I would say, I would dare to tell this. Why? Because we have modeled here a notch. We cannot measure in this notch with strain gauges to have a final verification if really the local stress, what we have calculated, is the real stress. I personally have the impression that in the case of the modeling, that we have calculated a little bit higher, by 10–15% higher notch stresses. Why this conclusion? The hotspot stress calculations were verified also by the strain gauge measurements. In the case we could have here a good contrast if the calculation was good. So I believe more that this result is more closer to the reality than this, and this is the conclusion that a little bit here in the modeling the notch stress was exaggerated. But this happens certainly as long as we calculate and we have no verifications, but as long as we are on the safe side, this is acceptable. With regard to the crack propagation, this seems good, but the results could be also more closer here to the value 1. Please remember the fracture mechanics data that we have applied here were not for r-1, but for r equals 0, not just only for the beginning phase, for the starting phase of the crack propagation, but for the whole crack propagation. So that means, in other words, if you would switch after 1 or 2 millimeter depth into another R ratio for the crack propagation calculation, we would be probably here more closer. But in all these three methods are very well equilibrated within each other. And I personally, when such calculations for such critical structures are made, I give always the recommendation, please don't rely only on one method, at least apply 2 methods and look if they are consistent. So this increases certainly the reliability also of what you calculate. And certainly in design, in fatigue design, we cannot only rely on numerical assessments. We need experimental verifications. But what is also very important is also to follow what happens in practice, what happens outside. Are there any failure cases? What can we learn from failure cases, and what can we transfer? And in this case, certainly, if we have all these three components, we can make reliable design. 500 years ago, a genius, an Italian genius, gave also a recommendation which goes also into this direction with regard to verification. It is Leonardo da Vinci. It is not quite the Italian that we speak today. It is the Italian of the Rinascimento, of the Renaissance time. But he says, Neil, I want to translate it for you. If someone makes speculations, don't believe him. Without any verification, don't believe to any results. This is also what Leonardo da Vinci says. So I think this is what we have to follow as engineers, and I'm at the end of my presentation. I thank you for your attention.